The human curiosity to unbox the unknown is unceasing, and that is why space explorations still fascinate us to this date. This project revolves around minimizing the cost of the rocket projection with the use of multivariable calculus. Now the question that arises is, why do we need stages in a rocket? When you burn fuel to get into orbit, you lose lots of energy to heat, the exhaust and atmospheric drag, so you actually need much more. But if you need more fuel, that means you need more rocket to carry that fuel. But this makes your rocket heavier, thus requiring more fuel, which requires more rocket to carry that new fuel, and so on. At the end of this madness, you need closer to 100 times the weight of your payload to launch. Not only is the payload a part of the mass, but the rocket structure and propellant also add to the net mass. Therefore, more changes in the amount of weight you're lifting greatly affect the size of the rocket you'll need. What happens in staging is that we throw away the excess bit of fuel tank that we no longer need after they are empty. If we don't do this, the empty tanks will just hinder the payload from reaching higher speeds. Staging is just a clever way of getting rid of unwanted parts of the rocket. In the project we designed, we have formulated and solved the math to optimize the total mass, taking into factors the mass. We have considered the math of two-stage rocket, but in practical cases there are generally more than 3 stages in a rocket. For example, Falcon 9 is a 3-stage reusable rocket, Saturn V is a 3-stage rocket, and Solve is an Indian rocket which is 4-stage.
So now let us try to understand the math of the project. First we will derive the rocket equation with the help of the laws of physics. By law of conservation of momentum, we know that initial momentum is equal to the final momentum. Hence, final momentum is equal to the sum of momentum of rocket and momentum of the gas. Here dmg represents small change in the mass of exhaust. So here is the math. So we now get to the final rocket equation as Vf is equal to u ln m0 by m, where Vf represents final velocity, u represents exhaust velocity of the gas, m0 represents total mass of the rocket, and m represents the final mass of the rocket. But this is just the ideal case. If we move towards a more practical approach, we get Vf equals to c ln m1 plus m2 plus a upon sm1 plus m2 plus a plus c ln m2 plus a plus sm2 plus a. Here m1 represents the stage 1 initial mass, m2 represents the stage 2 initial mass, a represents the payload mass, c represents the constant exhaust velocity, and s represents the structural factor, which is always between 0 to 1 and which is the ratio of ms upon m. Now, if we look at the total mass, it will be m1 plus m2 plus a. That means stage 1 mass plus stage 2 mass plus payload capacity. So now here, to simplify further, we will introduce 2 new variables, where n1 is equal to m1 plus m2 plus a upon sm1 plus m2 plus a, and n2 equals to m2 plus a upon sm2 plus a. Now, if we use some algebra and apply componendo and dividendo, we get these 2 equations. Equation 1 and equation 2. Now, one of the most crucial things observed is that the minimum value of m0 occurs at the same point as the minimum value of ln m0 by a. Hence, the function is always increasing here. As we differentiate, we get the answer greater than 0. So the minimum value of ln m0 by a will occur at the minimum value of m0 by a. So now, if we further find ln m0 by a, we get the further relation ln 1 minus s square n1 n2 upon 1 minus sn1 1 minus sn2. So, we have finally got our objective function, and we have also got our constraint function, which is gn1 n2 equals to cln n1 plus cln n2, which is also equal to final velocity. Now we'll bring Vf to the LHS part and equate it to 0. Now we will introduce the multivariable calculus and apply the concept of Lagrange multipliers. So now, by partially differentiating the function with respect to n1, n2 and lambda, we get the following 3 equations. Equating them to 0, we get our final result as n1 equals to n2. So at n1 equals to n2 is equal to n, we will get our optimum mass m0, where m0 will be minimum. So in this equation, Vf equals to c ln n plus c ln n, so which will finally give us n equals to e power Vf by 2c. if we further substitute that E equals to Vf by 2c equals to in place of n in the further equation, we get the following results. So now here we have got the value of m1 and the value of m2 in the terms of Vf and c and s. So m2 equals to e power Vf by 2c minus 1 upon 1 minus s e power Vf by 2c into a, and m1 equals to e power Vf by 2c minus 1 upon 1 minus s e power Vf by 2c into m2 plus a. Now let us suppose this e power Vf by 2c minus 1 upon 1 minus s e power Vf by 2c equals to k. So the minimum gross lift off mass will be km2 plus a plus ka plus a. Now this was just for the 2-stage rocket. It can also be generalized for 3, 4 and k stages. So following are the equation and mathematics for that part.